Hello, everyone. Welcome to the binary episode of the Day Zero podcast for this week. I'm Spectre. With me is Z. Apologies that we are a little late. Um, my sleep schedule is completely like it's done. I've never slept this late before, so yeah. Apologies for being so late. Z thought he might have gotten confused because of the DST, because like where he lives they don't observe it, but no, it's totally my fault for this episode. So. But yeah, we're here now, so we'll get into it. Um, and yeah, I guess we have a spot the Vuln challenge this week as well, so I'll let Z get into that, and then we'll jump into some of our topics.
Yeah, this week's Spot the Vuln is kind of a crypto issue. Um Fairly high level one, like some that should be or hopefully would be somewhat easy to spot, at least once you're familiar with it. The key thing that would kind of stand the code for those of you listening is effectively I just have a couple encrypt and a decrypt function, encrypting using AES, CBC. Not the best choice for CBC. There are better options, but fine. And in theory, it's being used to load a session. I just have it loading out of like a request. I don't have a ton of kind of surrounding code here. The real issue is to look at this crypto code and really notice that the HMAC value, or the variable that's called an HMAC, really is nothing more than a hash of the ciphertext. It basically doesn't actually have much of an impact. Since it's a hash of the ciphertext, it's provided from the user. That's kind of why I had the load session to kind of show user has control over all these values. Um, Effectively, the HMAC check does nothing, so there's no integrity validation on this, which means an attacker who can, create their own requests and send their own cookies, whatever, they would then be able to start doing. My thought was doing a bit flipping attack. With CBC, you flip a bit in one block, and you can cause flips in another, or you can cause flips in a resulting block. So basically, throw away one block and be able to decrypt a second one is whatever you want. You can look up about the bit flipping attacks, but that was kind of my thought. Yasner's in our Discord did also suggest perhaps going on a padding Oracle route because the crypto library here, PyCryptome, just raises an error. I don't have the code that would indicate whether or not that error would actually make it back out to the user, but definitely fair to kind of think something might go wrong and you might be able to turn that into a padding Oracle and try and get a decryption that way. But my thought with designing it was just going for the bit flipping attacks. An actual attack here, again, you would need more context on what you could do because you do have to kind of have that one garbage block. Because I was mentioning when you do, well, depending on how you want to go for the bit flips, but the attack I'm thinking of would. The main thing to really notice is that HMAC isn't authenticated. It's not a message authentication code at all. It is just a hash. And since the user can provide it, they can calculate their own because it's a hash of the ciphertext, not of the plain text.
HMAC without the Mac, basically.
Pretty much,
So
yeah.
yeah, and I was kind of talking to you about this a little bit after the show yesterday when we were talking a bit about the Spot the Vuln challenge, but I'll bring it up here as well because I see it a lot in like the PS4 scene and also just in general in InfoSec. Encryption almost feels like the magic wand that people point to, and they're like, "Oh, I'm secure. I did some encryption on this. Nobody can tamper with it. Nobody can take secrets from it or whatever." But a lot of the nuances of crypto seem to be lost. So I could totally see this like scenario playing out in a real world like situation. In fact, it has. I think we've covered some topics that have had this type of issue where they think that because they have something encrypted, it can't be tampered with or it can't be forged. Like they think it's authenticated without actually using something like HMAC properly. So
Yeah, it's
yeah,
definitely like I have seen this issue crop up before. I mean, not literally this code, but at least this issue where somebody was using thinking that all the message authentication code was basically a hash or like that sort of integrity check. Um it is a common problem. It's where, when we talk about don't rule your own crypto, I think some people also think that means, well, I'm letting somebody else implement AES, therefore I'm not rolling my own crypto. But no, like this is a custom crypto protocol, basically, that I've created in this spot, the Vuln, and that is something you should avoid. Um, let other basically pass it off when you can. There are sometimes issues with that, but yeah, I think that's a discussion for another day.
Yeah, it's an easy pit to fall into, though.
Yeah, I mean, unless you have a good background there, I just wouldn't recommend writing crypto code. Just let somebody else do it and take responsibility for it.
Yeah. All right, so with all that said, we'll get into our first exploit topic here, which is a post on exploiting a bug from Chompy. This was a bug in the IOU ring subsystem in the Linux kernel. Uh, Z mentioned to me a little bit before the show that this was reminded me that this was the same bug that we covered last year in September. It's hard to believe that it's been that long. But yeah, this post goes into a little bit more detail on IOU ring as a subsystem because when we covered it back then, it was I think it was like a mailing list message. So it detailed the vulnerability. We covered it at the time, but there wasn't any information or wasn't much information on the exploitation side of things. And you kind of had to know a little bit of the background of IOU ring to be able to comprehend that mailing list post. So here, Chompy goes into detail on IOU ring, some of the subsystems like and what it's for. For those that aren't really aware of it, because it is kind of a newer subsystem, it's based around doing performant I/O. It allows you to do copyless I/O with shared buffers, use fixed files, do batch I/O with IOVEX and such, that sort of thing. It's very interesting because where it's so new, there's a ton of movement in it. There's so many code changes that Z noticed that syscaller stopped fuzzing it entirely because of it, because there's so many bugs that come out of it but then are fixed or don't exist anymore because of changes in the next minor revision. So there's tons of movement in there, and thus it's an interesting target for bugs.
Well, I mean, I don't know if Syscaller stopped fuzzing it completely. I just know on their one Android build they recently disabled IOU ring. I didn't
Oh, I
look at
thought that was
anything
on
else, so I
more of
don't want
them.
to
Okay, fair
overstate
enough.
that at all because they
Fair enough.
might be fuzzing it elsewhere and just not with that particular build that I saw. That's it. I thought the mailing list was kind of clear, at least about what the vulnerability was. We did have a couple questions that we actually raised, I think, during or the last time we talked about in terms of how this was happening that Chompy does answer in this newer post. But the core issue, if you don't remember, and I actually even went back to my own summary from last time, um, basically you have a common function that might be implemented in the file system operations called read iter. And if that, which is kind of just an iterative read, when that isn't implemented, it will fall back to a loop RW iter, which just manually performs the same operation. And it'll kind of forward the rw.adder field as it's reading when it does that. So the problem being that in IOU ring, if you're using the op provide buffers, which will basically say like the kernel can pre-select and provide some buffers that'll be used for this read, um, that that buffer, that rw.adder value, is actually a kernel buffer rather than a userland buffer. And so later, when it goes and frees the buffer, thinking that it's now done with the operation and it could free it, it'll end up freeing this incremented value that's a kernel pointer rather than the userland pointer. So you're basically able to free adjacent memory because it increments it inappropriately, uh, reading on, and then tries to free it. So it was a really interesting primitive, I think. In kmalloc 32, that kind of comes up in the actual post. The post itself doesn't actually does spend quite a bit of time on the background, especially just on background of IOU ring. Spectre was kind of touching on this a little bit already, where it's an interesting subsystem in part because it's new, and just has so much movement going on that vulnerabilities can be introduced very easily. It's just like there's a new feature. at one point here, Chompy mentions like, and I was looking for some function that might let me do this one thing that would make the exploit exploitable, or make the vulnerability exploitable. Sorry. And it's like, yeah, and just like a couple months ago, they implemented the exact feature I needed, which was just being able to tell it what thread the kernel side work, the IOU rings worker thread should have its affinity on. So basically, what CPU core it should run on. That was added as a feature, like just in time to actually exploit this. Uh, so yeah, really quick movement. Going on with the actual thing here, she walks through the actual exploitation. Some of it's kind of familiar, so using like setxadder as one of the primary primitives just kind of gets spraying going on. One thing that I don't think I've really seen before is also using setxadder as more of the way of leaking another object. So what she did there for a leak primitive to just be able to leak any object out of KMalloc32 in this case, because it does rely on having this free primitive. So the initial primitive again is that being able to free adjacent memory, so being able to free other memory in KMalloc32. If you're not familiar, I guess I keep using KMalloc32. It's just for the 32 byte, all the objects of that size are going to be placed into KMalloc32 unless they're put into their own specialty cache.
Yeah, so kernel allocator is like generally pretty simple for most allocations. So in the slab, you'll just have like kmalloc32, kmalloc64, etc. The reason kmalloc32 was so interesting to me, and I called this out back when we covered the bug originally, is it's a very small cache. It's one of the smallest caches you can have, and generally speaking, as a rule of thumb, the smaller the cache, the more it's going to be used because you're going to have more smaller objects than larger ones generally. So you're going to have a lot of noise and movement in that cache, which when you're trying to exploit a use after free type situation where you're trying to get a reallocation, that's not a good thing for you because it's very possible that some other thread or process on the system steals that allocation away from underneath you. And depending on your bug situation, that could end up leading to a crash, or if you're lucky, you might just be able to try again. It kind of depends on how the data is used and how it gets corrupted. But yeah, KMalloc32 is it's getting tricky when it comes to like reliability and being able to reallocate effectively. So yeah.
yeah, so anyway, the leak Chompy turned this into was or I guess one thing I should also cover, if you're not familiar with a user fault FD being used kind of block set xadder, there's also a fuse trick that I don't recall where I first saw it. I think it might have actually been another one of Chompy's tweets where it got mentioned. Um, but basically using fuse to memory map a page that's going to be backed by like some fuse file, basically a user space file system fuse. Um, that's going to be backed by that. So when the kernel tries to copy information from it, it's going to end up hitting this userland application, which can then block it, which is important with setxadder because it will allocate a buffer for some data that you want to set into this extended attribute. Allocates a buffer for it, tries to read it with whatever you're trying to send in, and then sets the extended attribute with it, and then frees the buffer. So by being able to block it using this fuse trick now, because using the user fault trick is generally no longer available. So being able to block it there, you're basically just holding it open on that copy, and you can leave. You won't have it freed out from under you, so you can leave it open, or you can leave it allocated as long as you like, so it's useful for spraying. But so what this attack ended up doing is they would trigger this, so they would go through the normal spray, kind of setting some object there, have it be blocked using the fuse trick. Then using their vulnerability, they would free they would free that very same buffer again. And they cover their heap grooming, so they're confident that the buffer is going to be allocated kind of where they want it, and they're able to get that one as the one being freed. But they would then free their set X attribute or set X adder buffer, and then get that used up by some other allocation that or some other object that they wanted to leak, unblock it, and then set X adder will end up using when it copies it into the actual extended attribute, it'll end up using that whole buffer, including whatever it was just overwritten with because you had freed it. And then you can just use get extended attribute and read it at your leisure, basically.
That's a very cool strategy.
Yeah, I thought it was too, and I don't think I've seen that used before. It does. Part of that's probably because this primitive's a little bit weird. Like having this sort of free primitive isn't the most common thing to see. But yeah, I thought it was a cool way of going about getting that leak. And then once they leaked it, it was they went for like the task cred structure. So they went for I'm forgetting the name of the object now. It was something with the IO Uring buffer. Actually, I guess I'll just shout out. They do have a nice overview of the whole attack strategy at the top of the exploitation thing. So, oh yeah, the IO TCTX node structure contains the task struct pointer, so they're able to leak that. That contains the effective user ID, group ID of the thread. So that would be a target for overwriting. You target that data, say that you're root or owned by zero, and escalate privileges that way. Also the sec operations, which will give it's an operation structure, so plenty of function pointers. And that would be useful for actually breaking ASLR in the kernel. And then to actually do the overwrite on the task structure once they got to that point, took another trick here, I guess, that I'm not sure that I've seen. They targeted basically the BPF program structure, and this is why I'm not entirely sure. I know we've seen some BPF things, so I can imagine it getting used, but nothing comes to mind for it. Anyway, so they basically targeted, you'd have another socket open that had a BPF program attached to it, and targeted that, replacing it with their own BPF program structure. They cover a little bit about dealing with like JIT if it needs to be, or he's not, but basically using BPF to introduce the actual write primitive. Talks a little bit about the other option being like to create a ROP chain in the kernel would be a fair option. I don't know. My big takeaway on this one is really that set X adder trick that they use. I think that's a great, like a really cool way of going about it. The rest of it felt kind of like you would expect, except using the BPF is just kind of a newer trick that I think might end up seeing more frequently too, depending on how BPF actually gets hardened into the future.
eBPF actually shows up a lot in this episode. It's in like almost every topic, so we'll definitely be revisiting it. Yeah, no, the strategy, especially with the leak with through the X attributes, was really cool. And again, like you, that's something I kind of learned from Chompy's tweet a little bit before this post was put out, because for a while I wasn't even really aware that user vault FD was dead as a primitive. Um, so I was kind of saddened when I saw that. I think what they ended up doing, I think it was around like 5.1 maybe or something. Or it might have been a bit later, but yeah, they basically privileged it off behind capsys admin, I think. And that sucked because user fault FD was very useful for freezing those allocations. Because even if you ignore the reliability aspect with K free, because you know the main thing is you don't want to get that allocation freed while you're trying to reallocate, because it could end up being stolen and replaced with other data. But even beyond that, um, free uses the first 8 bytes of an object as like a metadata tag for the allocator. So if you are relying on those first 8 bytes for your memory corruption situation, especially if it's like a pointer or something, you could end up being screwed because the free will overwrite that. So in some cases, it's actually necessary to be able to freeze that allocation like that if you can't get a spray that doesn't free it immediately after, which Sedexatra does, unfortunately. So yeah, it was really cool to be able to see that kind of revived with Fuse. That was kind of a TIL moment, and there's a few things like that in this article that, if you're doing Linux kernel exploitation, there's some tricks in here that you should definitely like keep in mind, even if you're not looking at exploiting this particular bug or even a bug in IOU ring. There's stuff here that could be useful for other exploits too. So yeah, like a really well done post by Chompy here on GrappleSec. Um, and yeah, I answered some of the questions that I had back when we covered this bug originally. There was also something I was thinking of when you were talking about smashing the task structure to overwrite the credentials. Now, this isn't really mentioned in the article, but another thing you could kind of go for there is you could smash the address limit. And for those who aren't aware of what the address limit really is in the kernel task structures, whenever you do like a copy from user, whenever you use any API in the kernel that's going to be copying data from user space, the user space pointer is going to be checked against the address limit so that you can't try to be clever and pass like a kernel pointer as like the copy source or whatever, or the copy destination. So because of that, if you smash the address limit, you effectively can give yourself an arbitrary read-write primitive from wherever like data is passed into the kernel. The common one there is using pipes. Those can be very useful for getting arbitrary read-write. In this case, smashing the credentials is probably a lot easier. Though there are some cases where you might have to go a different route. I'm trying to think. I think Knox for Samsung phones. If you were to try to exploit this on a Samsung phone, if the circumstances lined up, I'm pretty sure Knox protected the credential structure. I might be wrong there, but I think it did have like a hypervisor checking that. So although it might check the address limit too, to be fair. But yeah, I just wanted to call that out. It's like there's some other potential routes you could go there too, with attacking the task structure. It's a very powerful object to have control over. So
Yeah, I mean, the other thing is this leak, like, there are definitely other things that could be targeted in general. Like, it was able to turn into a pretty powerful primitive of just being able to leak basically any object. Well, not any object within KMalloc 32. Um, like, just turned that into a rather powerful primitive. So,
yeah, there's a lot of different routes you can go, and that's another thing that kind of makes this exploit so cool is um, you could take this and play with it as an end day and try to see like how stable you can make it or what different kinds of strategies you could explore. So if you're looking to get into kernel exploitation and you want something to play with and something that uh, will challenge you to try to exploit it and maybe bypass all mitigations, this would be a good starting point. So Balika said on Samsung, TrustZone resets the CPU if it sees a root non-system process. Okay, interesting. That makes sense from their point of view, but I wasn't aware of that. There was actually a little bit of discussion around Android and Samsung Knox in particular that spawned off of this topic. It was mostly in the Twitter thread. You won't really find it in the post. Uh, but I think it. Oh wait, sorry, no, I'm confusing it with something else. I think. Um, I'm confusing it with Dirty Pipe because Fire 30 managed to get Dirty Pipe working on Android and demonstrated the POC of that. But that's separate from this, so my bad. Never mind. Forget what I said. But Chompy does call out in this article that this could be abused against Android, which I thought was a little bit interesting because from what I've seen with some of the configs in like the Android mainline, from what I can tell, IOU ring shouldn't be enabled. Um, so I would be curious on what devices IOU ring is shipped on because yeah, from what I've seen, I just haven't really seen it enabled. But
well, I think the
there's so much
main thing
fragmentation with
there,
the Android subsystem or in the Android ecosystem, so I could definitely see it being the case on some device.
Yeah, like I think the main thing there is more just like a user land process might have a hard time hitting it, but I think from like a Android service, they might be able to make the direct syscalls into it that aren't exposed.
Okay, that
Either
might make
way, I
sense.
mean, I'm not 100% certain on that. I don't really want to speculate on it either.
Yeah, okay, fair enough. Um, but yeah, Chompy kind of mentions towards the end, like, she believes that IOU ring is going to have an important impact on the future of Linux kernel security. I kind of agree, especially on the server and desktop side of things. The mobile side of things, I'm not totally certain because of the bit of discussion that we just had. But it is one of the major new subsystems to come into play. And because there's so much complexity and performance optimization that's going on, I think it is a subsystem that's going to have more bugs shaking out of it into the future. It's going to take a while to get to like a mature and stable state. So yeah, I think the conclusions there are are pretty a pretty good takeaway as well for the article. So
I'm not sure if we want to have this discussion right now. But Tompi does call out kind of the kernel's perspectives on security a bit and like security processes, calling out the fact that they'll modify the reported by tag because the email has security in the domain name, or removing the CVE identifier from a commit message, and basically making it harder to find fixing commits, which definitely aids in the fact that occasionally you have these fixes that are in the kernel that don't get a CV and thus don't end up actually getting sent out, or don't end up basically on anything downstream. I don't know. She calls out a few things there. I'm not sure if we want to talk about that at all.
yeah, I mean that's kind of funny. It reminds me a little bit of this tweet that like a meme that CTS posted for like trying to. I think this was in Linux as well, where they had a commit that fixed the use after free, but instead of saying that it fixed the use after free, it was like release memory in a more friendly way. It was pretty funny, trying to obscure security fixes a little bit. Yeah, Linux is kind of interesting when it comes to security fixes, and it's heavily influenced by Linus's perspective on it. Um, for those who don't know what that is, Linus's perspective on security fixes are basically that they're nothing special. They shouldn't be called out or treated as special. They're just regular bug fixes. And kernel developers' jobs are to fix bugs. So basically, he's kind of against the idea of treating security bugs as like special,
Well,
which
he does treat him
I
as special, though, by removing a CV identifier, saying, like, yeah, it fixes this bug, and this bug also has a CV. Like, that seems like something you would include as, like, yeah, this is just part of it. But no, they have to make it more special, more normal. Um, it seems like they
that's
are,
true.
like, there's no saying, oh, you're not treating it as special. It is special. And, the fact that they're hiding it is adding to that, not removing it.
Yeah,
I
you could. I could understand that perspective.
I mean,
Um,
Chompy kind of calls out in here like uh attackers are capable of looking through commits to find the hidden vulnerabilities, and they're incentivized to do so. Defenders shouldn't be burdened with this as well. And that's the thing, like a lot of people kind of look at some of these things as, well, we're making it harder for the attackers, so it's a win. But the thing is, like, it's making it harder for the defensive side too. And the attackers are a lot more incentivized to spend more time on anything, and do that. So it should be easier for the defenders, in my opinion.
yeah, it's a bit weird. Because basically what this is doing is it's security through obscurity, but trying to be deployed in like an open source way. Um, and the main argument for justifying security through obscurity is kind of creating that imbalance where it's like, okay, we at the company who are going to be fixing and finding these bugs have access, but attackers would have to do a lot of work to be able to get to the point of being able to audit like we can. Whereas in this case, yeah, it's kind of a double-edged sword, and it doesn't really benefit defenders that much more than it doesn't really hurt attackers more than it hurts defenders. So yeah, I don't know. I don't really agree with some of the philosophies when it comes to security by like the Linux dev team. Um, Saying that they don't want to assign CVEs to it and whatnot to make it harder to like write end day attacks. So I don't know. I kind of understand where they're coming from a little bit because the kernel is one of those things where people aren't actively updating it a lot on their server or something. Most people aren't checking for kernel updates and applying them as soon as they come out. Like that's just not a common thing. Um, Android is a little bit better where you have the updates kind of streamlined, but even then there's a big mess and a lot of fragmentation too. So trying to mitigate the discoverability of end days kind of makes sense from their perspective because the update ecosystem is not straightforward. It's not like Apple where you just get an update shipped and a lot of fixes come your way. Um, but at the same time, like she's absolutely right. Like attackers are going to go through those commit messages regardless. They're going to have strategies and tools in place to find them, and trying to hide them by removing like a security tag is just not really going to do very much. I don't think not against sophisticated attackers and tooling that are going to be doing this.
Well,
So
I mean, it does. Like, it does add on a bit of, it does add a layer of defense. I've often said this when it comes to security by obscurity. Like, it does do something. But it's also the fact that it is actively hurting the defenders too, because on the defense side, like missing the proper commits, not realizing something had a security implication, that's a big issue too. If it were just a case of like if that weren't the case, if they had some way of making sure everybody knew what a secure like which commits were security had security implications, you wouldn't necessarily see that same, I guess, downside from it, but they'd need to be maintaining something for it. And then there kind of comes down to the battle of, well, who are the defenders who get to know who's on the in, who's on the out. Kind of have those issues, but yeah, I don't know. I mean, I get where you're coming from. I get where that idea comes from. I know we've had similar discussions when it comes to Microsoft doing Patch Tuesdays to kind of hide security fixes in a bunch of patches. Like it's adding extra work, but the defenders are also being hit by that extra work, and it's the defenders who shouldn't be hit by extra work, because they end up spending a lot more time or sorry, their time is in a sense a lot more valuable because they're only able, usually not spending anywhere near as much time or not incentivized to spend anywhere near as much time as an attacker would be. So when you have those things that kind of hit both, it benefits the attacker.
yeah, it basically comes down to whether or not you think the trade off is worth it, and I don't like it's yeah, like you said, it impacts defenders too much and doesn't do enough against attackers. So yeah, in my opinion, it's not really worth that trade off. I don't really agree with the maintainer's perspective on this, and I have a feeling you like. I think you kind of share that same view. So
Yeah, I do. Um, Also, that Mr. Gabe mentions also never stops people from selling info from the inside on something like that, which is a fair point too. I mean, insider threats. When you have this sort of special or secret knowledge, it could be sold off that way, so it's creating an issue that may not have been an issue otherwise. Real RBX says, I don't see what the purpose it would serve other than stopping bots that scrape or whatever. Part of it is exactly that, though. The bots that would scrape and just immediately find this thing is a CV. Where isn't it getting applied to? Um, like that sort of automation is absolutely in use.
yeah. All right, so I guess we can get on to our next topic here, which is a post from Exodus Intelligence on a use after free in the Common Logging File System for Windows, or CLFS, which is a driver that applications can tap into to access logging capability. It rolls its own file system where records are stored in sectors, which are stored in blocks, which are atomically read and written. Um, there is a bit of background that needs to be understood before getting into the vulnerability. This is quite a dense post and goes into a lot of detail on the file system side of things. Mostly the background info that's necessary is uh, relevant to the base log files and the metadata blocks they contain. So basically, base log files contain three different types of metadata blocks: control records, which have some information about the layout and extended area information, which will be relevant for the bug; base records, which have symbol tables and other information like security contexts; and truncate records, which have information regarding sector changes for truncation operations. Now, another noteworthy thing here is each of these metadata blocks is then like duplicated or shadowed. So you have 6 metadata blocks per file, 3 of each type, and then shadows for those blocks. And the purpose for that is basically to have a backup so that that information can be restored in the event of like a torn write or something. You can also have these blocks be extended depending on how the control record is set up and what fields look like for the block start offsets and such. Um, Under normal operation of like a stable log file on the disk, it's expected that the extension state for all the blocks are going to be 0, which is kind of where we start getting into the bug here. Which unfortunately, I don't think the bug is like super well summarized in this post. You kind of have to read through everything and understand um, like the paragraphs bit by bit. You really have to dig into it, but the bug is in the open path for opening and reading a base log file. So when opening a base log file, the metadata blocks I mentioned earlier have to be read from disk and loaded into memory, which is done through this acquire metadata block function. So it'll allocate into pool memory for that block metadata, then read the sectors from the disk to fill in that data. What's kind of important there is in this scenario, the attacker has control over the file contents, and thus it has control over those metadata blocks. And thus they also have control over the control context and the extend context, which contains the index of the block that would be extended or flushed if the extended state is set. So with some specially crafted data in the extend context, um, and if you can get the extend metadata block descriptor function called by setting that extension state, you can enter this branch that I think. Let me just get it on screen for those watching because there is a lot of code snippets here. I forgot to note down exactly which one it was. Cool. I think this might be it here. Yeah, so there's this path. Oh, yeah, this site highlights everything when you click in the code snippet, so I'll try not to do that. Um, Although I can't. Okay, well, here we go. Sorry, that was a bit of a struggle. Okay, so yeah, on this branch here, if the PB image is not null for the block that you're flushing, it'll free the PB image field from that block. But then the problem is just under that, like if statement under that if block when that's taken, the CB image field for the block that you're flushing gets reset from the shadow block. And as I mentioned earlier, the block and the shadow block are duplicates of each other, meaning the PB image field will point to the exact same location that was just freed. So you kind of get this dangling reference reintroduced into the record through the shadow block, which then opens up the use after free possibility, which I believe they take advantage of here as a double free. So I think they kind of just exploit this path twice, get it double freed, and when you get a double free, that gives you a very useful primitive because it basically gives you the ability to do a targeted use after free on that pool. They get into some information about how they exploit that with the Windows Notification Facility, or WNF, to derive primitives for getting a reallocation gadget and eventually smashing a token. I don't want to go too far into that because it does get into the specifics of WNF, which I'm not familiar with because I don't do Windows stuff.
Yeah, I think we
Um,
actually
so
covered some of this with WNF. I think we might have actually been covering another vulnerability that Exodus published. It might have been somebody else, but I do recall us dealing with some of the primitives they were gaining out of there. Unfortunately, I wasn't thinking about that, so I'm not sure which episode that would have been on.
yeah, um, Windows is kind of interesting because they have some movement in how pool memory is managed and some hardening. So this is like talking about exploiting it on newer versions of Windows since 19H1, which had some fairly significant implications when it came to heap shaping and whatnot. and there's not a ton of resources, I don't think, for some of the newer versions of Windows and attacking the kernel heap like this. So um, the Windows notification facility seems to be the like golden egg of where to derive primitives from right now. Um, there is also a bit more nuance as to how to get into this UAF scenario, depending on like the context values and stuff in the malicious file. Um, you can kind of see those if you go through the pseudocode snippets if you're interested. The post itself, though, doesn't really go into a lot of detail on that. It was a little bit tough to try to get to the meat of the bug in this post because yeah, it's mostly just like decompilation code snippets from F5, and you have like 25 code annotations. So, um, yeah, I would recommend if you just want the summary of this bug to check out our website and the summary that we have, because there isn't really a summarized version on this post. Um, but yeah, like I said, they use WNF to to exploit it. They try to overlap some state data objects, which they use to get a out of bounds read write into adjacent state data objects, which they then use to change the size of one to get a backing data to overlap with a token. Abuse the use after free part of it again to, or sorry, they resize the object and then they use the out of bounds write to smash that token for their new process. So again, kind of that idea of primitive chaining. They start with their use after free or double free. They move that into being able to corrupt heap data for the WNF, which they then are able to smash a token with, which is the end goal on Windows, is always going to be smashing a process token to elevate it. So yeah, I mean, a lot of information here and a lot of code snippets on the common logging file system seems to be one of those areas of Windows that's being looked into a little bit more. I think there when I saw this post mentioned on Twitter, there were some other people who had collision on this issue and also had some other issues in the common logging file system. I'm not sure if those have already been detailed and we just missed it, or if they're yet to come. So I guess we'll find out as time goes on. But yeah, this almost seems to be a little bit like an IOU ring area of Windows in the way that it's actively being looked at. So uh, yeah, kind of a cool bug. It is a very involved bug in that you have to understand a lot of the context and the control flows going on here to really appreciate how this bug could be abused. That said, it is also kind of simple in the way that it's literally just freeing this field and then reloading that field in an unconditional like jump. So it's a little bit weird how that code is set up. Obviously, we do just have the decompilation code here because it's Windows, it's closed source. So we don't really get the insights as to why they might be doing that on the code side of things, but yeah, it is some very weird code. And if I saw just that one bit of code in like a code review or something where it was freeing it and then it was reloading it with like a shadow block version, um, yeah, that's a pretty big red flag and was obviously a bug here. So
Well, I feel like the key thing there is that it's not expecting the shadow version of it to actually have the exact same values as what were there. They do kind of introduce the whole scenario because of the unexpected metadata kind of leading to it. So I imagine the default state, those would have different pointers. It's just as soon as you have the user control, that's where they're able to kind of introduce that.
yeah, kind of break some of the assumptions that were made.
Yeah.
All right, so we'll move into the hardware side of the episode where we have some speculative execution bugs cropping up again. Our first one here is an AMD branch predictor bug detailed by GRSec. This one was discovered when trying to verify speculation safety for an optimization of reuse attack pointer return hash sequences, which is basically GRSec's version of software CFI. It's not super relevant what it does beyond the fact that in these like ROP sequences, they have a move ABS instruction at all the call sites as part of like a debugging snippet in it. So it'll do this move ABS to move into like REX, I think it is. And then they have like a bunch of int3 or breakpoint instructions. Um, but in typical operation, those instructions will never actually be executed. There's an unconditional jump above it, which will just jump over those instructions. But what they wanted to test here was it possible for those debug instructions to be executed speculatively? And, spoiler alert, it was. So when they went to verify it, they found on Zen 1 and Zen 2 CPUs it could be executed speculatively due to straight line speculation. SLS was coined by an ARM white paper, where sometimes an instruction or some series of instructions immediately following an unconditional jump um, would be executed. Unfortunately, I couldn't really find details on exactly why this happens, but on ARM, it was possible in some edge cases for it to occur with indirect unconditional control flow changes. So, like a return or a jump call on a register or dereferencing register, something like that. And this could potentially be exploited if some useful gadget was found that would taint the cache in a way that was useful, so that you could leak secrets. On AMD CPUs, it turns out it was vulnerable to this too, but it was actually even more impactful than it was on ARM, because on AMD it could be used for direct control flow changes too. Um, if you could force a branch misprediction on direct unconditional branches, which you could. The reasoning for this is kind of interesting. Basically, on x86, the branch predictor has to predict both the condition and the target. And the target aspect is kind of a weak point, because to do that, it relies on the branch target buffer, or the BTB, to start fetching instructions. But if you flush the BTB and there's no BTB entry when it goes to look it up, it'll just kind of fall back and default on predicting that the branch is not taken. I'm guessing they probably did some, statistics and found that more often than not, if there's not an entry, that's because the branch is never taken, so it's more performant to just assume that. But that kind of opens the door here for the straight line speculation, where if you're relying on that unconditional jump to take place, it could just keep speculatively executing because it thinks, well, branch is never taken, so just keep going. Um, Now, although this is a hardware bug, you can very reliably, according to GR security, get the CPU to mispredict these unconditional branches and trigger SLS. The impact, though, is somewhat limited, just like the ARM situation was. The speculative window was limited to 16 bytes of x86 instructions, and was even further restricted by the types of instructions you could run. Um, they didn't really go too deep into that, but basically it comes down to the microcode complexity impacting the execution time. If your execution time got too long, you would kind of fall out of the speculation window. So you had to be very careful about what instructions you would choose as part of your gadget were for wherever you wanted to attack. You would also have to rely on those gadgets being present at all. Though this article kind of covers where this attack could be viable in a real world scenario, which is basically using eBPF filters in the Linux kernel. Basically, they wrote a filter that would include a gadget around a kernel pointer load. Um, I don't want to go too deep into that, because this starts talking about the how certain instructions impact the cache lines and kind of getting a cache line oracle, which I don't fully understand. Basically,
So
what they did
you can
was
kind
they
of
just
you can
go ahead.
get deep into this, but I was just want to say, like, it just kind of comes down to the fact that are basically just ignoring that and pointing out this kind of similar to some of the ideas with like JIT stuff, where you would use a JIT to introduce the gadget that you wanted. I mean, similar concept here. They're using eBPF to do that. The specifics of all of the speculation stuff, I think, is beyond both of us. And we've spent some time talking about, I know, when some of the first speculation issues landed. Um, but sorry, I did kind of interrupt you there. So
Yeah, no worries. I was going to go into a little bit of the BPF filter and kind of what it did, but without being able to explain the cache stuff that was happening at the cache level, I don't think it'd really be relevant anyway. Um, or I wouldn't really be able to add a lot there. But you can kind of check out the BPF filter. Like, they have the full snippet there in the article, so if you want to check it out, it's there. But yeah, basically they set up a gadget after this load of a kernel pointer into a BPF register in such a way that you could leak bits of that pointer through the cache. They couldn't leak all the bits of the pointer. I think they could only leak like bits 7 through 49 or something like that. I don't remember the exact. Let me just see if I can find that. Yeah, so bits 6 to 47, so I was close. But when you're talking about kernel pointers, that's more than enough to be able to break KSLR, because the upper bits of a kernel pointer are going to be consistent, and the lower 5 bits are not really relevant for breaking KSLR. So, um, yeah, this is like a practical attack. You could definitely use this in some way, shape, or form in like an attack chain. Uh, but yeah, whenever you get into like these speculative execution type bugs, uh, there's a lot going on under the hood that isn't immediately obvious with like the code that you're looking at or what you're expecting the CPU to do, because there's so much stuff going on at the microcode level, and a lot of the time those, like what's going on at the microcode level and the mitigations and stuff that are at that level, are kind of hidden and kept proprietary. It's not public information. They're in like these manuals that are heavily, like the access to it is heavily restricted. So yeah, you need to do a lot of research to fully grasp the what's happening at kind of the really low level under at the CPU microcode level. So unfortunately, can't comment too much on that. But the takeaway here is just the fact that that straight line speculation can happen at all. You don't really need to understand exactly why it happens, but it's possible to force a situation where those instructions after an unconditional jump can be executed speculatively and leak cache data. So,
Yeah, I mean, you can kind of like summarize this as just the fact that in some cases they would speculate on the instructions following that unconditional jump, which to actually quote a Linux kernel maintainer, doing so would be idiotic. Of course, like as Spectre explained, like there is a little bit of reasoning behind it because of just that default, and that's why it ended up happening. But this whole idea was actually speculated about when they're thinking like, would it try to speculatively execute the pad instructions or the padding? And you get that comment there. The CPU doesn't speculate down past the unconditional control transfer. Doing so would be idiotic, which seems like a fair statement for like assuming the CPU isn't going to do anything stupid. But at the same time, that's also just like, software people like myself. I'm not trying to say that I'd have been smarter about, I'd have thought this was a reasonable assumption, not really understanding how all of the hardware ends up working in the first place. Like, when it comes down to modern CPU engineering, I am largely entirely lost. And, you know, that information doesn't really matter on like a day to day basis, but if you kind of understood that's like, well, there are some cases. I mean, obviously, not everything does this speculation, but it becomes a lot more understandable, I think.
yeah, and it just comes down to something we kind of talked about before with optimizations from like compiler optimizations, but at the hardware level. Um, CPU manufacturers they're starting to hit that point where it's really difficult to get massive performance improvements without having to do like tricks, and these special optimizations. And you notice that because there's some people that have tried to disable these performance optimizations entirely in order to avoid the speculative execution attacks, and the performance loss is enormous in some cases. So you can kind of see like it it's the evil that comes with the benefits of trying to do this performance optimization and doing this branch prediction. Um, and again, it comes down to those trade-offs. But in this case, like a lot of people are willing to take that trade-off for the increased performance at the risk of sometimes having these speculative execution bugs that could leak data through the cache. Um, now, again, like with this case, I think it's worth noting the Zen 3 CPUs were not they didn't manage to get this working on newer Zen 3 CPUs, so it's only Zen 1 and Zen 2. And beyond that, they pointed out the eBPF scenario, but in a lot of scenarios where an attacker is more restricted, it would be very difficult to take advantage of this because you have to rely on gadgets already existing. I can't think of many situations where you're going to be able to create your own gadgets to do something useful in the kernel like that. Um, so
Wouldn't a browser perhaps be another one? Like just a
You're
JIT, any
thinking like
real
JIT?
JIT engine. Yeah, that's kind of what I'm thinking. I
It
don't know
might
for
be.
sure, but that's kind of my first thought.
It might be. So browsers have done some mitigation on speculative execution when it comes to JIT specifically. That said, I'm not sure what all of those mitigations entail, so I can't really comment on that too much. It could be. I don't want to rule it out either.
Yeah, that's just like one of the only cases I could really think of being able to introduce your own code into a running and your own native code in particular into a running application are things that end up getting jitted or things that kind of have that runtime execution.
Yeah. But in a lot of cases, it's going to be tricky to take advantage of this, and that's kind of been the case with a lot of the speculative execution bugs. So, and yeah, I guess we'll get into our last speculative execution bug
Yeah,
and the last topic of the episode.
just before you do, I will also clarify, like I am kind of just tossing JIT out, like, yeah, you could just JIT the code you want. Like it is, even if it is possible, it's not that easy to do it. To just cause whatever you want to be created, especially in this case where you're trying to get code after an unconditional branch. Seems like something like if there is that unconditional thing, the JIT itself may be to kind of optimize certain things out of what you're trying to do. So it would definitely be a lot more tricky than how I'm just saying it as, yeah, just JIT it. Like I'm making it sound a lot easier than it probably would be. So just to clarify slightly, I realized it would be difficult.
All right, so we do have one more speculative execution based attack, which is another branch predictor attack called BHI, or branch history injection, which extends on the idea of branch target injection, which has been known about for a while, colloquially known as Spectre v2, which is where you train the branch predictor on an indirect branch to speculatively execute a branch incorrectly and side channel the cache to leak data. One of the mitigations introduced and that was refined to mitigate branch target injection um, was detailed in 2018, and it was called Enhanced Indirect Branch Restricted Speculation, or EIBRS for Intel, or CSV2 for ARM. And its goal was to try to isolate these indirect branch predictions of more privileged contexts from less privileged ones, in an effort to prevent you from being able to inject branch predictor targets into a more privileged context. So, you know, like trying to inject branches into the kernel branch prediction from user space or something like that. The details of how that's implemented are not very public or well known. Again, you're starting to talk about proprietary code. The only prior work that was done was from Exynos. I never know how to say that name. It's the Xenos CPUs for ARM that are used in like mobile devices and whatnot. Um, they thought that ARM's CSV2 was similar enough to EIBRS and what it provides, in the way that it was probably similar in implementation as well. The authors thought that was a reasonable assumption. So, because of ARM being open source, they were able to get some information on how that mitigation worked. So, in the Xenos case, the branch target buffer basically had tags that would get hashed and used as a key to encrypt the branch targets. So, kind of the idea of PAC actually when it comes to branch prediction. You're encrypting or tagging those pointers, and those tags are going to be validated when the branch target buffer is referenced. Um, the problem here, though, is the way that tag is calculated, because the way the tag is calculated is they take the branch source address and they combine it with um, some analysis of the branch context, which is basically a history of previously executed branches, and that history is stored in the branch history buffer. Now, the researchers here thought that the branch history buffer might not be isolated properly like the branch target buffer is, because of performance concerns, because you need branch history going across a privilege boundary to accurately make a branch prediction. So user history, or history from user space, would hold heavy influence and control over the branch history buffer, at least for some of the early predictions that are made. This in turn gives you control or influence over the tag, which you could then bypass this mitigation entirely, because the mitigation is based on that tag's integrity and being able to validate and ensure that a user can't forge uh, a branch target to be injected. But since they have control over the branch history buffer, they can influence that tag and kind of walk around that mitigation. They tested this and discovered that, yep, Intel and ARM CPUs that used EIBRS and CSV2 respectively were vulnerable to branch history injection for cross privilege boundaries, whether that be user to kernel or guest user to host kernel. Basically, any like privilege boundary you can think of there, this could cross that boundary. Um, they were able to get this working on both in-place and out-of-place kernel targets on Intel CPUs by way of tag collision. And the difference between in-place and out-of-place is basically that in-place is the same indirect branch, whereas out-of-place, I believe, is any indirect branch in the kernel. Since they have control over the BTB tag, they can just influence it to equal the tag of whatever they want to direct execution to. They didn't get this reproducing for out-of-place kernel targets on ARM CPUs, though, and they don't really go into much detail on why, nor did they really seem to want to investigate that too much. And they call out the fact that it's just because the ARM ecosystem is so much more fragmented in its implementation of how the branch history is used. So it'd be a bit of a rabbit hole that they'd have to dive down and cover a lot of different implementations, and they just didn't want to do that, which is fair enough. But yeah, I mean the main point of this paper is the fact that the branch history buffer is relied on for calculating that tag, and that isn't really isolated. So yeah, the reliance on it is weak. Uh, and I think there would be some massive performance implications if they tried to isolate the branch history buffer. So it's a bit tough to handle from like Intel's perspective, and that's kind of been the case with a lot of the speculative execution bugs, because a lot of the cases when you try to handle them, the way of handling them is introducing something that causes a massive performance hit.
Just get rid of
So
speculation, right?
yeah, that's the safest course.
I mean,
Um,
it's a weakness at the design level. So whenever you have that, like, it's hard to fix. And that's software or hardware. I mean, even more so in hardware because it's like the architecture. Like just at this level, it is hard to fix there. Like I don't fault them at all, or even for taking the, in a sense, even having the shortcut in the first place. It's one of those things that you can kind of spot the issue just by looking at the architecture and the fact that that isn't isolated. Therefore, it is an entry point for some sort of issue.
yeah, and kind of backing up what I was saying a little bit before, um, the paper does bring up some like potential mitigations you could use to like counteract this. So they mention here, uh, sorry, let me just find it. Yeah, in the absence of simultaneous multi-threading or SMT, we verified that a complete flush of all previous BTB entries with IPBP on x86 can be used as an effective countermeasure. This strong barrier prevents unprivileged layers from interfering with higher privilege predictor modes. However, this defense introduces a huge performance overhead since all privilege levels are affected by every flush. So again, like this could totally be mitigated and um, killed off, but it comes at the expense of performance, and people have kind of shown over the last couple of years they care about the performance a lot more. Um, Intel kind of recommended just disabling eBPF entirely because again, this paper kind of touches on how this could be abused with eBPF. Um, and I guess, yeah, seems the best way to prevent yourself from being hit with speculative execution attacks is just make it so attackers can't create gadgets. So disable JIT, disable uh, eBPF. No,
Stop
but
using a computer, honestly.
I mean, yeah, that's the way to be ultimately safe. But yeah, I mean, like I said, it's kind of tough to mitigate. They're disabling eBPF from an unprivileged context does kind of make sense for a lot of people, though.
That's
It
just a
is one of those
Linux thing
things where,
too. Like that's just reducing attack service on Linux, not even speculative execution. That's just like there's such a huge attack surface there in user namespaces. Just disable them.
yeah. I was just reading out of chat.
Yeah, I
Dirty
was
Harry
gonna.
One was asking some questions. Did you want to bring it up?
Yeah, I was thinking we could. If you're done on this topic, though.
Yeah, I've pretty much said everything I can on this topic. So
Yeah. So Dirty Harry one. I'm not sure if we'll be able to talk too much about here. Have you looked into the Nvidia, I guess breach at all? I don't really pay a lot of attention to breaches, so I don't know the details about it.
So no, I haven't really looked at the Nvidia leak. I don't even have like access to it. Um, but the it seems the
Do you know
question
what was
was
stolen? Yeah. So the question's kind of just more about like what damage could have been done with it.
so if I remember correctly, I could be conflating this with the Samsung leak. There's actually been so many leaks lately that it's it's hard not to conflate them. But one of the two, either the Samsung or Nvidia leak, contained uh like trusted execution environment, like trust zone applet code, which could have some fairly significant implications when
That
it comes to
was
bugs. Um,
I don't think that was the Nvidia one.
you think that was Samsung? Okay, it might have
Yes,
been.
because I remember us talking about that one.
Okay, so when it comes to Nvidia, it's tougher to comment because I'm not exactly sure what was contained in the leak. If they do have some of like the code that's running on like the privileged, uh, I don't want to say hypervisor. What's the like watcher code or whatever? There could be some significant implications there. Um, that
Okay,
said,
Blika mentions two driver signature keys. Um, and those work on Windows 7, so that's something. Code
there you
sign-in
go.
keys could be used to sign malware or, well, malicious driver that could then be loaded on Windows 7. Mentions works on Windows 7 only, so could be used there. If you're still running Windows 7. um, with a lot of source code, like it does make the vulnerability research easier. Dirty Harry one kind of asked a little bit about the idea of like he had malware somewhere in here. Attackers from Nvidia could modify data, make it look certified. Wouldn't there be a way to infect part of AMD if there was malware? See, like I feel like this whole idea that, and I skipped a lot for those of you listening. Um, feels a little bit far fetched to think that Nvidia would have like malicious code in their own stuff in case they're breached so that somebody else can take advantage of, or like they can take advantage of it against somebody who uses it. Um Possible, yes, but very, very unlikely in my mind. Of doing something like that. I think the big thing is what, assuming all of this information is legitimate, just what attackers could actually do with this rather than something actually needing to be pre-existing.
Yeah. So we've kind of talked about this a little bit with things like Windows before, where the source code is closed off, and what does that mean for security research? So obviously, like security research still happens against closed source targets. You can still do VR. It is a bit tougher because you are limited to only like the binary view. You're losing a lot of context with not having the source code. So yes, this could have some implications when it comes to attackers. That said, when you're talking about something like Nvidia, where it's kind of running on specialized hardware, the Nvidia drivers could be interesting to look at because a lot of the times when you're looking at like GPU driver, the kinds of bugs you're looking for, like in the IOMMU, can you get DMA where you shouldn't be able to, or something like that? And in those cases, you're looking for bugs that are um, a little bit strange and have to cross the bridge to the hardware a bit more. So yeah, the source code could enable finding of those bugs easier, and maybe even just exploiting of those bugs easier by being able to explore the area a bit more. But I don't think it's like super significant. Like, there's been some leaks in the past that I've seen, like with Valve, where people have thought as soon as it leaked, oh shit, like everything Valve is going to be packed now or something. Like, just having the source code leak doesn't automatically mean that there's going to be big attacks that are going to come out of it, but it does make it easier for sure.
I guess the other thing is like with Valve, I remember us talking a little bit about that one. Valve, there's a lot of instances where people are running Valve software over the internet where it's going to be exposed online, like to other players in a game, for example, where an issue in the engine could potentially perhaps be exploited by a remote attacker. something like Nvidia being, your own local hardware, the drivers, the attack surface, privilege escalation. It's there if you already have that foothold, but there isn't that I can think of. I don't know. Maybe Nvidia is doing some things I'm just unaware of. I definitely am not all up to speed on everything that they've got, but a lot of it is kind of that second layer of an attack. Privilege escalation. Maybe on phones, consoles, things like that, and not things that would actually be too risky to an actual user. Obviously, we did just talk about the driver signing keys. That does matter. Like keys like that definitely need to be secured.
Yeah, and Balika mentioned Samsung Leak had 13,000 private keys. Most of them test keys, but still. Yeah, it sounds like the Samsung leak was a lot worse than the Nvidia leak was. That said, without having access to those leaks, I shouldn't comment too much on that, I guess. But um, yeah, whenever you have these kinds of leaks, it is, the security discussion always gets brought up. Um, the point that you called out is very good, though. Like the fact that, unlike Valve, this is not really a remote attack surface. You kind of need that local foothold. And when you're talking about like Windows, for example, uh, I think there's probably easier targets you could use for privilege escalation than a GPU driver or something like that.
There's
There's a
some
lot of
stupid
really
drivers
weak
out there.
drivers on Windows. Yeah. You could target like an anti-cheat or like an antivirus driver probably a lot easier and get a lot more success. So, um, and then the other thing is too, where this is NVIDIA, you're also limiting your attack out of the gate. Like you're kind of doing this with if you try to go after like an antivirus driver too. You're relying on an antivirus being installed, but this is even more limiting in a way because if you're attacking a target and they're not running an NVIDIA GPU, like they have an AMD GPU or even an iGPU, then you're kind of screwed as an attacker. It's not really an ideal case. You generally, especially if you're going for a wide sweeping attack, you would want to attack a driver that's going to be common amongst a lot of people. Nvidia would be kind of common. Like I'm not saying Nvidia GPUs are not used or anything. Like it is they have a heavy part of the market share, but um, I think even then you would still want to go for like a more common driver. Just hit something like Win32K, which is obviously going to be in all versions of Windows. So
Yeah, I mean,
yeah,
malware developers, I could see it being part of, random exploit kit drops in, something like that. There's enough people with it that it could be worthwhile on there, that it could be seen as somewhat valuable by malware developers to do that. Because, I mean, they're just generally going to be looking for, they'll have like a low, I guess not an exploit kit, that would be more in browser going for it, but yeah, I mean, there is a targeting question, but if you're going at it like that on malware, could have several vulnerabilities installed on it, and then just like, hey, which one works on this system? But at that point, you've also just got the key. I don't know. I mean, I could see some room for it. Like, it's not like there's no, there's plenty of people running NVIDIA hardware. So, I mean, and on nice machines that are kind of worth something if they compromise. I can kind of see it being somewhat valuable in that sense. Like, I mean, it's not like an Android exploit or something, but it has its place.
yeah, and like Balika mentioned, like I think most workstations has no dedicated GPU. Like that's kind of the thing. Like Nvidia is very common in like the enthusiast space where people are using add-on boards. They're using an AMD or an Nvidia GPU or whatever. But there is also a lot of the market where there is no add-in card being used. It's kind of just relying on like an iGPU or in a server like no GPU. Like it's just there's the when you
Yeah, but my
factor in all
point,
the potential devices, yeah, NVIDIA is less common than you might think.
well,
That
more
said,
my
it's not
point
like
though,
non-existent.
yeah, so more where my point is though is like, they don't only have one exploit, they can have multiple exploits. So one might be for
Oh, for
Nvidia, one
sure.
might be for something else. Like it just using that sort of connection. Um and the fact that people that do have an Nvidia device do have their external, or not external, their dedicated GPU. That's a nice machine for malware to compromise if they want to say do some mining. So like it has that extra value just because of that too. That's at least where I see it. Like I have not been involved with any malware development to really know the calculus that goes on in deciding such things. I'm purely just kind of speculating, uh, based off of what I think somebody might find valuable, not from any actual experience.
Wow, not even a real hacker, never written malware.
Sorry, yeah. I mean, I did write, way back. I wrote a lovely virus for a school computer that would pop out the CD tray and offer you a drink holder. But that's
I
the
remember
rite of that kind of
passage
shit type
too.
of virus thing to write.
Yeah. Um, that is actually a fair point that you raised with the mining, though. I hadn't really considered that, but I mean, yeah, there's definitely malware that's targeted on the mining side of things, and when you're talking about GPUs, yeah, it would make a lot of sense to target uh, the GPU drivers. So that's yeah, that's a fair point. I hadn't really considered. Um, but yeah, uh, it's hard to really comment too much more on that. Where like it's leaked material, so even if I had looked at it, I don't think I'd really want to talk about it very much. But I haven't even really looked at it, so
Yeah,
I'm
neither
just
have
going
I.
off of like a meta discussion and talking about like
Yeah.
some points that have been raised with past leaks mostly. All right, but yeah, that's basically all the topics we have for the episode. So Z, unless you have anything else you want to bring up before we wrap it up, we'll go ahead and kick it off here.
Nope, I've got no shoutouts this week.
All right, cool. So that's all we have for today. Thank you to everyone who tuned in. The VOD will be up on YouTube and Spotify and other platforms tomorrow, as always. Feel free to follow our Twitter and join our Discord for notifications for when we go live, or if you just want to discuss any of the topics or anything you find interesting. We'll be back next Monday and Tuesday for the Bounty and Binary episodes, respectively. Hopefully on time, and we'll see you next week.